If you recall, in the last lecture we were discussing binary diffusion. Earlier to that we had focused only on diffusion of trace species, that is, we had assumed that when the concentration changes, for example, or when there is a flux due to a concentration gradient, there is no center of mass velocity that is generated due to that concentration due to the flux, right. However, if you have a binary mixture in general, the molecular weights of the two species will not be equal. And if you have, as you know, in kinetic theory of gases from the ideal gas law, it is the molar density, the number density of molecules, that is a constant when the pressure and temperature are constants, because the number density of molecules or the number of moles per unit volume is related to P by kT, where P is the pressure, K is the Boltzmann constant and T is the temperature. So, the number of moles is a constant, and therefore, if you have two species, you will have equal moles of one species going in one direction and equal moles going in the other direction to maintain a constant pressure whenever binary diffusion takes place. And when you have transfer of moles in opposite directions, there is a net transport of mass as well. The reason is because the two species have different molecular masses, and therefore, you have to write down the equation for the diffusion in terms of the mass concentration or the mass fraction. And we had discussed that the last time. Okay. I had defined for you what are called mass average quantities, okay, what are called mass average quantities. Okay. The concentration of the two species in a binary mixture is the mass of that particular species per unit volume. So, you have two different species Ca and Cb. The total mass density is the sum of the mass densities of both of these species. The mass fraction is the fraction of mass of A molecules in the mixture. So, you define the mass fraction as Ca by rho and Cb by rho, and the sum of the mass fractions has to be 1, which means that the sum of the derivatives has to be 0. Okay. The flux, as I said, is defined differently in the case of binary mixtures. Okay. It is defined as d into rho into d of w by dz usually. Okay. That actually follows from a thermodynamic description, which I will not have time to go in detail in this course. So, this is the flux, plus there is also a flux because of the mean motion, because of the center of mass velocity. Okay. The flux of A molecules due to the center of mass velocity is W A rho into V z. Okay. And if I define, if I express rho V z, the mass flow rate, as the sum of the flow rates of the two species, okay, I get this expression, and therefore, you can see that you have a flux appearing on the right side as well of both A and B. Okay. And by symmetry, the flux for B has to be given by this second expression here, where we substitute A for B and B for A. Okay. And you can show by adding these two up that the diffusion coefficients dAB and dBA are exactly the same. So, that is a mass average description. Okay. The other possible description is what is called a mole average description. Okay. You define a molar concentration, number of moles per unit volume as C, okay, the mole fractions as Wa and Wb, and the molar fluxes as Jaz and Jbz. I have used capital letters here for the molar quantities, okay, and Ca and Cb are the molar densities of species A and B, and the total molar flow rate is the sum of the molar flow rate of the two species. And then you get constitutive relations that are very similar to what we had earlier for the mass average quantities. Okay. And you can once again show that the diffusion coefficients are symmetric, dAB is equal to dBA in this case as well. Okay. So, that is the modification that one has to make for binary diffusion. Okay. So, I have Jaz and Jbz on the right side as well, okay, in this description. You can imagine that for multi-component diffusion, the number of such species increases. Okay. So, that is the reason for simplicity we have restricted attention to 2 components. And now you need to know something about how these vary. Okay. How does the total flux or the flux of one species, how does it vary, okay, with position or time, okay, in order to be able to close these equations, because these are coupled equations which you can close only by solving the pair of equations for JAZ and JBZ, and then you get nonlinear relations, okay, for the rate of change of the mass or mole fractions. We had considered one problem earlier, and that is I have a column of water, okay, a column of water, I am sorry, a column of air with water at the bottom, okay, and that water is evaporating into the air through this column, this tube that is 15 centimeters in length. Assume that dry air is flowing on top, so that the concentration is equal to 0, and the concentration at the bottom is given from the vapor pressure. Okay. At 25 degrees centigrade that we are considering, the vapor pressure is about 3.15 kilopascal. That comes from thermodynamics tables, and the diffusion coefficient we have assumed is 2.2 into 10 power minus 5 meter square per second. Equation for the flux of water. Okay. It is depends on both on the flux of water and flux of air. Okay. Now, why does air enter into the column? That is because as the water evaporates, the level of the water decreases, and as the level of the water decreases, some air has to come in to occupy that space. So, there has to be a flux of air downward also. However, the volume of water that is evaporated is much smaller than the volume of water vapor that results. Okay. There is a factor of about 1000. Okay. The liquid density is about 1000 times or 800 times the density of gas, and because of that the volume of water that is evaporating per unit time is much smaller than the volume of water vapor that is coming out per unit time. Consequently, the volume of air that has to come in to replace the liquid water per unit time is much smaller than the volume of the water vapor that is coming out per unit time. And if you neglect the decrease in the height of the water surface, right, because the volume of water is much smaller than the volume of the vapor, then the flux of air is equal to 0. Okay. Okay. And therefore, this provides us an explicit equation for the water flux, okay, and that explicit equation can be solved quite easily. It is a first order differential equation for the water flux. We had solved it to get an equation for the flux as a function of the water concentration in the column. Note that this equation is a nonlinear equation because it has a 1 minus WW here. Okay. So, the flux is not a linear function of the fraction of water. Okay. It is a nonlinear function of the water fraction. Okay. Okay. So, this can be solved to get the flux as a function of position. It has one integration constant because it is a first order differential equation. At z is equal to 0, we know that the concentration of water is equal to the saturation concentration. Okay. We had calculated that, okay, the mass fraction of water in the vapor at the surface is going to be I am sorry, the mole fraction of water at the surface is going to be equal to the ratio of the vapor pressure and the atmospheric pressure. Okay. The ratio of the vapor pressure and the atmospheric pressure is going to be the mole fraction of water at the surface. So, at the surface z is equal to 0, the mole fraction of the water is Ws, and I can use that condition to determine what is this constant of integration and get an explicit relation, okay, for the relationship between the water mole fraction and the flux of water. Okay. At the top surface, we know that the mole fraction of water is equal to 0 because it is dry air, and therefore, at z is equal to h, W has to be 0. Okay. So, you get that this relation between the flux and this expression for the flux. Okay, you get this expression for the flux. Okay. Now, the last step is to actually find out what is the flux. Okay. The last step that we need to do is to find out what is the flux. For that, we need to know the molar concentration. Okay. The molar concentration C is equal to P m by you can choose it either as R or kBt depending upon, I am sorry, there is no m here, this is the molar concentration. So, this is equal to P by RT. P by RT when expressed in terms of moles per unit volume. If you express it in molecules per unit volume, it would be P by Kb times T, okay, the number of molecules per unit volume. P by RT is in moles per unit volume. So, this is 1.013 into 10 power 5 okay, pascals is the pressure, okay, and R is equal to 8.314. Okay. 8.314 is in basically in energy per Kelvin. Okay. So, this is joules per mole per Kelvin. Okay. Into the absolute temperature that we had was 298 Kelvin. Okay. And this turns out to be 40.9 moles per meter cubed. Okay, this is 40.9 moles per meter cubed. Okay. Pascal is force per area, and in the denominator the energy is force into length. So, you get a 1 over meter cubed here. Okay. So, that is 40.9. Okay. And if you recall is equal to 40.9 moles per meter cubed, okay, into the diffusion coefficient. The diffusion coefficient we had was 2.2 into 10 power minus 5 meter square per second, okay, divided by h, which is 0.15 meters, into log of 1 by 1 minus the mass fraction, the mole fraction at the bottom surface is the saturation mole fraction is this. Okay. And you can do this calculation and get what is the moles per unit time, and the total number of moles, right, the mass per unit time, mass evaporated per unit area into time is going to be equal to JWZ into the molecular weight of water, that is 0.018 kg per mole. Okay, this gives you mass evaporated per unit area per unit time, and if you do this calculation, this will turn out to be equal to 3.4 into 10 power minus 6 kg per meter square per second. Okay, so, that is the mass evaporated per unit area per unit time. Okay. Okay. So, this is the mass per unit time. Now, we need to find out what is the change in height of the interface. Okay. How much does it evaporate per unit time? Okay. And the change in height can be calculated from the relation that the density of water, okay, this is the water density, not the vapor density, into the area, right, into delta H, okay, the change in height in a time delta t has got to be equal to the mass flux JWZ. Okay, so, this is the mass flux, okay, into area into delta t, okay, which means that delta H by delta t is equal to JWZ by rho W. Okay. Is the ratio of this the mass flux and the density. Okay. So, this is equal to 3.4 to 10 power minus 6 kg per meter square per second divided by 10 power 3 kg per meter cubed. Okay, which is about 3.4 into 10 power minus 9 meters per second. Okay. That is the 3 nanometers a second is how much the height decreases by approximately. Okay. And if you work it out for a full day, this comes out to be about 0.29 millimeters per day. Okay. So, this is one example where I showed you that even though there is this complication that the flux depends upon the species, there is a coupling between the fluxes of each species because of the center of mass velocity. In this particular case, because the volume of air coming in was much smaller than the volume of water that was getting evaporated, we were able to set the air flux equal to 0 and solve this equation explicitly. Okay. The other case where you have an explicit relation between fluxes is when, for example, a reaction takes place. Okay. So, let us look at a problem where there is a chemical reaction, and because of the stoichiometry of that reaction, there is a relationship between the fluxes coming in and going out. Okay. This is the formation of iron pentacarbonyl. Okay. The reaction is that the iron in the solid phase plus 5 CO gives you FeCO5. Okay. That is the reaction at the iron surface. This iron pentacarbonyl is actually used for treating things like anemia and so on. Okay. And one of the ways of making it is by the gas phase, the reaction of solid iron and carbon monoxide. Okay. So, the situation typically looks like this. Okay, I have iron here in the solid phase, and then above this, okay, I have a height of about a centimeter, and I have carbon monoxide flowing past. Okay. So, what happens is that the carbon monoxide comes down, reacts with the iron surface, and then iron pentacarbonyl is produced. Okay, iron pentacarbonyl is produced in this case. Okay. This takes place at a temperature of about 400 degrees centigrade. Okay. And for the present, we will assume that the reaction is very fast. Okay. So, that the carbon monoxide concentration at the surface is equal to 0, because the carbon monoxide instantaneously gets consumed, okay, when it is as soon as it comes to the surface, and the iron pentacarbonyl is equal to 0. The molar concentration of iron pentacarbonyl is equal to 0 in the gas stream. That is, the gas stream is fast enough that it carries along all the iron pentacarbonyl with it. Okay. And this area of the reactor, I will assume, is equal to 100 centimeter square. Okay. It's equal to 0.01 meter square. Okay. Now, in this case, the relationship is that for every 1 mole of iron pentacarbonyl that is coming upwards, there have to be 5 moles of carbon monoxide coming downwards. Okay. That gives us a condition for the relationship between the moles of these two species. Okay. So, the condition basically is that the flux, the molar flux of CO divided by the molar flux of FeCO5, okay, is equal to -5, because for every mole of iron pentacarbonyl that is going upwards, there have to be 5 moles that are of carbon monoxide that have to come downwards just from stoichiometry. Okay, just from stoichiometry. Okay. And this relation can be used in the equation for the flux. Okay. So, for example, if I write the molar flux J Fe CO5, okay, is equal to minus d times the molar concentration times d W, the weight fraction, by dz, okay, plus WFeCO5 into JFeCO5 plus JCO. Okay. JA is equal to minus DC into dWA by dz plus WA into JA plus JB. Okay. A is FeCO5, B is CO. Okay. And this relation can be used to express the flux of FeCO5 in terms of the flux of CO. Okay. Sorry, the flux of CO in terms of the flux of FeCO5. So, I will get plus WFeCO5 into okay, JFeCO5 minus 5 times JFeCO5. Okay. So, I get a factor of minus 4 here. Okay. So, if I write this equation, I will get J of minus dC dW FeCO5 by dz minus 4 W FeCO5 into J of FeCO5, okay, iron pentacarbonyl. Okay. So, I take this to the other side and I will get J of FeCO5 into 1 plus 4 W FeCO5 is equal to minus dC dW. Okay. And now I can solve this equation. Okay. I multiply throughout by dz by dC. Okay. So, I will get J FeCO5 dz by dC is equal to minus dW FeCO5 by 1 plus 4. Okay. Which implies that J FeCO5 by dC times Z, okay, integrate once, is equal to minus ln. Okay. I should note here that I had put a log over here. Okay. Throughout this course I will be using only natural logs. Okay. Throughout this course I will be using only natural logs. So, for making it more precise, let me write this as ln, okay, for the natural log. Okay. Because there is a prospect of getting confused between the log to the base 10 and the natural log. So, I will use ln here, okay, for natural log to avoid this confusion. Okay. So, I will use ln of 1 plus 4 W FeCO5 by 4 plus an integration constant, okay, plus an integration constant. Okay. This integration constant I can determine from the condition that at the bottom surface, okay, at z is equal to 0, at the bottom surface I said that the reaction is very fast. There is no carbon monoxide. Mole fraction of carbon monoxide is equal to 0. Therefore, mole fraction of iron pentacarbonyl has to be equal to 1 at that bottom surface. Okay. At z is equal to 0, the mole fraction of iron pentacarbonyl has to be equal to 1, okay, which means that from this relationship the left side is from this relationship the left side is 0, okay, at the bottom surface the left side is 0, and the right side is minus log of 5 by 4. This implies that I, the integration constant, is equal to ln of 5 by 4, natural log, okay, of 5 by 4. Okay. Now, at the top surface, okay, at the top surface, okay, z is in this direction, z is equal to 0 as the iron surface. The top surface is at z is equal to h, okay, the top surface is at z is equal to h, where the height is equal to 1. Okay. I told you that at the top surface the gas flow is sufficiently fast that the concentration of iron pentacarbonyl in the gas is equal to 0. Okay. As soon as it gets generated, it gets swept away by the gas. Okay. So, if the flow is sufficiently fast, the mole fraction of iron pentacarbonyl has to be equal to 0 at the top surface. Okay. Therefore, I get the relation J iron pentacarbonyl into H by D times C is equal to minus ln of okay, is equal to okay, minus ln of 1 by 4 plus ln of 5 by 4. Okay, where I is the integration constant that has been substituted over here, and I have set the mole fraction of iron pentacarbonyl equal to 0 at the top surface. Log of 1 is just 0. Okay, log of 1 is just 0. Okay, so I just get log of 5 by 4. Okay, so therefore I get the flux of iron pentacarbonyl is equal to D times the molar concentration by H ln of 5 by 4. Okay. And I forgot to mention here the diffusion coefficient of iron pentacarbonyl was equal to 2 into 10 power minus 5 meter square per second. Okay. That was the given value. Okay. So, what is the concentration of the molar concentration at 400 degrees centigrade in this case is equal to P by RT, atmospheric pressure, okay, divided by 8.314 into 400 plus 273, okay, that is 673. Okay. Okay. 400 plus 273, this is carried out at 400 degrees centigrade, so this is 673. This is equal to 28.8 moles per meter cubed. Okay. Substituting that in the expression for the flux, I will get the flux of FeCO5 is equal to 2 into 10 power minus 5 into 28.8 divided by 0.01 meters. Okay, so, let me put the units there. Okay, I should have been a little careless here. Should always put the units. This is in Pascal. This is in 8.314 joules per mole per Kelvin into 673 Kelvin. Okay. And this gives you the answer of 28.8 moles per meter cubed. Okay. And over here I have meter square per second into 28.8 moles per meter cube. Okay, if you put the units in, you will be able to immediately see that everything, the dimensions are all consistent. Okay. Okay. Into this factor of log 5 by 4 into log of 5 by 4. Okay. This turns out to be equal to 2.3 into 10 power minus 2 moles per meter square per second. Okay. So, that is the flux, okay, 2.3 into 10 power minus 2 moles per meter square per second. Okay. Molecular weight of iron is equal to 206 grams per mole, which is 0.206 kg per mole. Okay. So, you can multiply this to get the mass flux. Okay. The mass flux of FeCO5 is equal to J of FeCO5, the molar flux, times the molecular mass. Okay. Okay. And this turns out to be 4.77 into 10 power minus 3, okay, 10 power minus 3 kg per meter square per second. Okay. That is the mass flux, and the total production rate is the mass flux multiplied by the cross sectional area. Okay. You recall the cross sectional area was 0.01 meter square. Okay. So, therefore, the production rate is equal to 4.77 into 10 power minus 3 kg per meter square per second into 0.01 meter square, that is the area. Okay. 0.01 meter square is the area. Okay. So, and this gives you 4.77 into 10 power minus 5 kg per second. Okay. 4.77 into 10 power minus 5 kg per second. So, this is an example of a case where we have binary diffusion, where there is a significant flow rate generated, mean flow rate generated by diffusion, because number of moles coming downwards has to be 5 times the number of moles going upwards, and that makes a significant contribution to the mass flux, and that ratio is obtained only from the reaction stoichiometry. Okay. And we had simplified the problem so that there is instantaneous reaction at the bottom surface. Iron pentacarbonyl concentration is 0 at the top surface, and if you know the diffusion coefficients, then we can just use that and the molar concentration at that particular pressure in order to calculate what is the production rate. Okay. So, this is an example where the mean velocity due to the diffusive flux is important, has to be taken into account, and if we do that, we can predict what is the rate of production in this case in the limit where the reaction is very fast. Okay. So, these are two examples that I did of binary diffusion, where the relationship between the flux and the concentration gradient or the mole fraction gradient is in general nonlinear. Okay. You have the equation of this form. Okay. You have the equation of this form, okay, which contains the first derivative of the mole fraction in the z direction as well as the mole fraction itself due to the mean flow. Okay. So, you do not get a linear relationship between the flux and the gradient of the concentration when there is binary diffusion, and there is a mean flow generated, okay, in this case. And in this case, so this is the way that one would solve this and get a solution which is which in this case is an exponential solution. Okay. The mean the variation in concentration is related to the flux is related to the log of the mole fraction, okay, in this case. So, these are two examples of binary diffusion where we cannot neglect the mean flow. Next lecture we will revert back to considering linear relationships between the flux and the force, but incorporating the effects of correlations in the balance equations. I will show you the cases under which this can be done and what are the limitations. We will continue this in the next lecture. I will see you then.